right, thank you very much for the introduction. Let's start. This paper deals with the gas metal welding with stainless steel, both Austenitic and Duplex 1. Well, the idea is to start working on the processes rather than metallurgy. So the basis on this presentation will be try to evaluate the both steels based on the process rather than metallurgy. Austenitic because it's the most well-known, and Duplex is, okay, many people researching, let's see what you can find about it. Well, spattering definitely is, can be a problem if when welding with short circuit metal transfer, and we may have problem. Okay, material losses are not that high, I must say that, but the problem with extra labor and the extra time to complete the welding definitely is a problem from spattering. Okay, and definitely affect both quality and productivity. Well, the idea of reducing spattering is that we can try to accomplish that by trying to establish better weld parameters regulation and setup. But we can work on welding process, the parameters itself, depends on if it's a constant voltage or current, constant current power source, the shielding gas composition, travel speed, and parameters in general way, let's say that, and both filler and base materials. But in this particular case, I try to deal more with metal transfer, especially short circuit, because we say spattering anyway. In that case, for gas metal arc welding. Well, and it comes from the short circuit from the periodic contact between the metal drop and the wire and the weld pool. And let's try to establish a relationship between regularity of the transfer, the metal transfer, and the spatter reduction. I would like to point out that we are not saying stability of the metal transfer. We are saying regularity, because stability is a little bit more complex, which is stable, which is unstable. Here we talk about regularity, which means independently of the time, we have the same frequency or the same open arc time, the same short circuit time. We talk about constancy here, not stability. Okay, stainless steel is widely used. Definitely is a worth material to be studied. General applications. Also, we try to present a qualitative analysis of spattering for Austenitic and Duplex stainless steel when welding with short circuit metal transfer in gas metal arc welding. And by doing that, we try to present and correlate an index. We have been developed for carbon steel, and in this work we try to do that for stainless steel. That's called IVCC. It's just an index based on both open arc time, both open arc and short circuit times, periods, let's say that. And try to say that index represents the regularity of metal transfer. Let's try to see if you can manage to do that. And this index comes from the analysis of the electrical signals. Okay, our parameters, reference voltage between 14 and 22 volts. Is a common range for short circuit transfer. Wire feed speed of 2.8 meters per minute. Which give us 125 amps, and 2.8 meters per minute, which give us 155. In fact, okay, this is a conventional constant voltage power source, but it's important in welding that we try to keep the current as constant as we can. So we change the contact tip work distance for that wire feed speed. So by changing the contact tip work distance, we try to keep the same current. So we keep the wire feed speed and we keep the current. How can we manage to do that? By changing contact tip work distance. So contact tip CTWD change during the welding. So we keep the same 125 amps or 155 amps within a range of 5 amps. So we consider that it's the same value from 120 to 130. Shielding gases, most used for, let's say, those two wires, argon with 2% of CO2 and argon 2% of oxygen. And for purging, we use pure argon. The filler metals were the standard ones, 308 LSI and 2209. It's the most we use for the base metal is we use, which were the 304 and the 2205 for duplex. So that's the weld metal that we use is a small bar, stainless steel bar with 3/8 of an inch, 10 millimeters softly, and 200 millimeters of length. So the idea is to deposit the weld pool only in that small bar, so we can collect all the spattering. I'll show you in a moment. Okay, how can we do that? Oops, sorry, I have here. Oh, wonderful. Because we weld inside this box made of copper. It's just thin sheets of copper. We place our small bar there, and after we weld, we collect all the spatters within 3 ranges. Beyond 160 meters, between 81 and 160, and closer than 80 millimeters, 80 mils. So we can have bigger spatters, small spatters, as farther than the weld bead, the smaller the spatter gets. So we have, let's say, an idea of if you prefer or if you don't prefer to have bigger spatter, or if you prefer to have a smaller but farther spatter. So that's a small box just for collecting. We weld within this box, let's say, and after we use a sieve to collect the different size of the spattering, and we can measure both percentage of the spattering, the position efficiency by weighting the welded bar before and after the weld. We have the percentage distribution by range of the size of the spatter and the size of spatter itself. Okay, the index that we propose is a simple relationship between standard deviation of short circuit time, standard deviation of open arc time over those times themselves, which means that the higher the times, or in that case we prefer the smaller the standard deviation for both short circuit time and open arc time, the smaller those standard deviations, the smaller will be this index. Okay, we can try to make, let's say, a more complex index. Perhaps I prefer to have a large short circuit time or a large open arc. You can place some weighting values here to separate short circuiting and open arc time. But it is an index that have worked really well for carbon steel, and we try to use for stainless steel. But you can't use this index alone. We have to establish a frequency of metal transfer, let's say a cut frequency, a frequency that below that you don't consider the metal transfer, because when we are at short circuit metal transfer, if we increase the voltage, we end up with globular metal transfer. And let's say in the limit, globular metal transfer has a zero time of short circuit. So 0 means 0 deviation. So you may consider the index perfect for globular transfer. So in order to avoid that we reach globular transfer, we just consider a frequency, a limit for frequency that, okay, if you are going to 10 hertz, 5 hertz, 12 hertz, depending on the Y-feed speed, droplet diameter, and electrode diameter. So depends on those parameters. You say, okay, below 10 hertz, I don't consider that short circuit. I am already getting to globular metal transfer. So just a frequency to not confound and not mix up globular metal transfer and short circuit transfer. Just for that let's say cut frequency. It's just a frequency that, okay, below that I will not consider that transfer as short circuit. So we have both a minimum, so because we end up with a big droplet size and a globular, as well you must have a maximum frequency, because otherwise you start getting to a let's say too drastic or short circuit transfer, you know, too much material for that weld pool. You end up rolling the wire itself and you got really messed. Let me show you the